All right, so the first one here, we see a square root. Now this one's in the denominator, but that's not necessarily going to be a problem. So we'll do our u substitution. So u then is going to be then 1 minus the 4x squared. I can take my du for that. So just taking the derivative of both sides, the derivative of u is du. The 1 goes to 0, and I'll end up then with negative 8 x dx. And again, we always introduce then that differential when we take in the derivative. And I see in my numerator, I have then the x here and the dx, so I can replace that just with that, but I don't need that negative 8. So the negative 8 I'll move to the other side. 1 over negative 8 du then is equal to that x dx, and then that will then be the substitution I need for that top piece of the integral. So my integral now is just going to be 1 over the square root of u, and then times negative 1 over 8 du. The negative 1 over 8, as before, I can pull out in front of the integral sign here, and I just end up with the integral of, and let's put actually in exponential form, u to the negative 1/2 du. So that one there, I can then just add the 1, and so it'll go to positive 1/2, and so I get 1 over 8, and then I'll get 1 over 1/2, and you can just jump to 2 for that one as well. U to the 1/2, and because it's indefinite, of course, always then the plus c. So this will go to 2, and then 2 times 1 over 8 will give me then a quarter. So I get negative 1/4 u to the 1/2, or square root u plus c, and then I'll put my u value back in, the 1 minus 4x squared, and so then I'll get negative square root of 1 minus 4x squared all over top of 4, and then plus c. So this next one has a trig function, and the term in the bracket inside the trig function then is going to be a good candidate for your u substitutions. And so we'll have u equals w minus natural log of w. So the derivative of u is du, the derivative of w is 1, and the derivative of natural log of w then is just going to be 1 over w. And then I have my differential there as well. So we see that in this function here. And so we have then the 1 minus 1 over dw, or 1 over w, and then times dw. And so all of that, underlined in red there, can be replaced with du. And so what that's going to mean for my integral then is that my integral then just becomes cosine of u, and then times du. And that's certainly a much easier derivative to take, easier antiderivative to take. And so the antiderivative of cosine is just sine, and so it's going to give me sine u, and then plus c, and then all I need to do is put my u substitution back in there. And so I'll get sine of w minus natural log w, and then plus c. And you can leave it in that form, and that's your antiderivative. So what we'll notice with this one here is I get this 1 plus 2x term showing up in both of those. Now that is the term in the bracket, so it's going to be a good candidate for u substitution. And I can see that I can actually end up substituting it in for both. So I'm going to end up then with u equals 1 plus 2x. I can take the derivative of that, and that'll just be 2 dx. So my du equals 2 dx. And so this one here, I do just have a dx. Now these are constant values, so I don't need to replace those. I don't actually have any x's there that I need to replace. So I'm just going to do a straight swap between my du and my dx. But this constant 2 then does need to be moved over because it doesn't show up really in this equation. So my 1/2 du is just going to be equal to dx, and that's the swap that I'm going to be doing. Now for my limits of integration, I'm going to put negative 6 in for u, and so it'll just be 1 plus 2 times negative 6. And so for the u to the negative 6, that'll just give me negative 11. For the other one, I'll have u to the negative 2. It's putting negative 2 into here, so 1 plus 2 times negative 2. And so that'll, of course, give me negative 3 then as the limit of my integration. So what I'm going to do here is I'm going to actually split this up into 2, and then I'll apply the differential then to each of those individually. So just rewriting this, I have negative 6 to the negative 2. That'll be 4 over 1 plus 2x cubed dx. And I can subtract from that the integral of negative 6 to negative 2, 5 over then this 1 plus 2x and then dx. And this will be a little bit easier to see how the differential is going to get replaced there. So I will replace my limits of integration and then those u substitutions to shorten this a little bit. So this will then go to negative 11 and negative 3. this just becomes 4 over top of u cubed, but this differential dx is going to get replaced with 1/2 du. Now I'll subtract from that my second integral, and still between -11 and -3. This will just be 5 over u, and again this dx needs to be replaced with 1/2 du. And so do remember to include that 1/2 in both of those terms when you're replacing those ones. So we can clean this up a little bit. -11 over -3. Now 4 divided by 2 is just 2, and I can actually take that 2 outside the integral, and I'm just left with then u to the -3 du. I'll subtract that. Now this one here, 5 over 2, I can take that outside of this integral, -11 to -3, and that just leaves me then with 1 over u du for that one there. And so then I can solve for each of those integrals as they go. This first one will just be the power rule. So remember we're adding 1, so -3 plus 1 will give me then a -2. So I'll have 2, and then u to the -2, and then also over -2. And I'll subtract from that. The 5/2 again is going to stay out front as it is. And then now this one here, remember we can't do the power rule on u to the -1. This just becomes then the negative log of u. And then the whole thing will be solved between then the -11 and the -3rds. And now at this point, all I need to do is put those values in. So the 2 over -2, that's just going to go to -1. My u value for the first one will be -11 to the -2. We could put that in the denominator as well. That would certainly be fine. And then I'll have 5/2. Now, one thing with this one here is if you check your formula sheet, it's actually natural log of the absolute value of u, which will be important because I have negative values here. So I have natural log of the absolute value of -11, so just the natural log of -11. And I'll subtract from that. Again, -1. Here I'll have -3 to the -2. Could also again just have it 1 over -3 to the 2 would be fine as well. I'll subtract 5 over 2. And again, it's the absolute value, and so I'll end up taking the natural log then of the absolute value of -3, which of course will then just be 3. And it's important you put the absolute value sign in this one here, because of course you can't take the natural log of a negative number. But if you put that absolute value sign in, it is just on your formula sheet, that will give you those values. Now for this one, we'll leave it in the exact form, so we'll just group this term and this term together. That will end up giving me then 112 over top of 1089 if you group those ones. And then the other two I'll just keep as two separate ones. Again, they have different natural logs there, so there's not too much I can do with those. So I'll have 5/2 natural log, and I'll just change it to the natural log of 11. Two negatives there, so this ends up being positive. So 5/2 natural log of 3. And that's a good way to leave it, just in now exact form. Now my last one, again, I have two parts. I have then the e to the y between the 1/2 and 0, and I have 2 cos pi to the y. Now what we'll notice for this one here is this e to the y, I can take that integral without actually doing any substitution. So I'm going to solve that one separately from this one over here. So as before, I'm going to actually just separate this integral just up into the two terms. So I get 1/2 to 0. This is going to be e to the y. And I'll add to that, and I should have a differential there, so dy. And then I'll add to that then the integral, again from 1/2 to 0 of 2 cos and then pi y dy. Now this first one is perfectly fine just as it is. I can easily solve for that integral, and so it's only the second one that I need to do the substitution for. And you can do a substitution then just for part of the integral and leave the other half alone if you can split it up into the different terms. Now my u substitution here is just going to be this term in the brackets, again from the cosine, and so it's going to be pi times y. So if I do my derivative here, the pi is just a constant multiplier, and so I'll get pi dy. I'm really just trying to solve for this dy, and so I'll get 1 over pi du is equal now to dy. Now when I look at my limits of integration, I'm going to have u times pi of whatever y is, and I have 1/2. So I'll have pi over 2, and then 0, and so I'll have 0 for that. So my u to the 1/2 is just going to be pi over 2, which will be one of my new limits of integration. and then u to the 0 is pi times 0, and so that one's going to be 0. So I'll change my integral for this one here. So I will actually just rewrite this one over here, but we're not going to do anything with this until we are ready to take the antiderivative. And so we'll leave that one alone because we don't need to make any substitutions there to solve that. This one here, though, we will do our substitution. So first of all, with my limits of integration, so it'll be pi over 2 to 0. And then here we'll have 2 cosine, now just u. And then 1 over pi du for that one there. So we'll solve this integral right away. So the antiderivative of e to the y is just e to the y. And so I'll be left with e to the y, and then solve between 1/2 and 0. And then I'm going to add to that. Now I can take this 2 pi out just as a constant multiplier there. And then I'm just left with the derivative of cosine of u, which is going to be sine of u. And that one now is going to be solved between pi over 2 and 0, because again they have then different limits for my integration. So I can just put these values in. This will be e to the 1/2 minus e to the 1, or sorry, e to the 0, which will just be equal to 1. Now I'm going to add to that then each of these. So I'm going to have 2 over pi sine of pi over 2, and I'll subtract from that 2 over pi sine of 0. That's just going to be a matter of solving those. So e to the 1/2, that's just root e. You can use exponential form or radical form would be fine as well. E to the 0 is just 1, and so I'll get negative 1 for that. My sine of pi over 2 is just going to be 1, so I'll have 2 over pi times 1, and sine of 0 is of course 0, and so that just goes to 0. So I'll have root e minus 1 plus 2 over pi, and that would be a perfectly fine place to leave that.